Okay, to show the equivalency, let's first look at what the right-hand side means. So we want to show on the right-hand side, we want to have, say, a ball centered, the unit ball centered at 0 with the radius 1. So this is a unit ball in X, in the space X. And it will be mapped to this ball, which is T of B0, 1. Okay, so this is B0, 1. And that is T of B0, 1. This is in the space 1. Okay, and the 0 is interior point means that we want to show that there exists a ball here that is U0 delta. Okay, so that's how the 0 becomes the interior point. Okay, so what we want to do here is to show that the T is an open mapping if and only if the 0 is the interior point of this T of B01. Okay, I'm sure these two are equivalent. Okay, so let's do that. First, if T is open mapping, we want to show this is true. Well, this is kind of obvious because this is a ball, right? It's the open ball. So if a T is open mapping, that means this is open set. And because 0 must be inside this image, since 0 is mapped from 0 here. So T0 must be 0 since T is linear. So this 0 is a point in the open set. That means 0 is the interior point, and that means there exists such a ball that is completely inside this image, completely inside here. Okay, that's why it's obvious, given that T is an open mapping. Okay, so that's the first this direction. Now let's see the other direction. So we want to show that if 0 is the interior point of this TB01, then we can show that T is an open mapping. Okay, to this end, let's first think in this way. If T, say so we know there exists some delta such that the U0 delta is inside the T of the image of B01. Suppose we know this. Then we know that if you're shifting 0 to x, you move to x, then we have B of x, 1, after the mapping. Because T is linear, so it will also be mapped, this ball will be mapped to the Tx delta. Okay, we'll have this. Okay, and also if I multiply this 1 by any r, I scale this ball larger or smaller, I will have the corresponding one on the left as well. This is all because T is linear. Okay, and we will have this. Okay, so if we know this, then we can see that once we have an open set W inside X, and then for any point X in here, I know because W is open, so X must be interior point. That means there must be a ball centered at X with the radius R. Okay, so now let's keep that in mind. This ball must be inside the W. And then let's consider the TW. This is the Y, this is TW. So apparently X is in here, is mapped here as well. So the TX here, the T of BXR will be somewhere here. Okay, this will be this will have radius r delta with center tx. This one is the u tx. Sorry, will be the t of. Oh, I should say this. Let's say in this way. So this will be the y, and this set here is tw, and the x, the b xr ball is mapped to here. So this center must be tx. This ball here must be t of b xr. Okay, and we know that this is not necessarily a round ball, but it's just an image of a ball. And then we know that this UTXR delta is inside of this. That means I have a ball right here, again centered at x, and this is a real ball inside y with the radius equal to r delta. Okay, and this means that the tx is the interior point of the tw, because you found this ball inside a larger one that is also inside tw. So this ball here is the neighborhood of tx, and that's in tw. So this implies that tx is an interior point. So for every point in tw, it can be written as t times some x, t applied to some x. And this point is an interior point, and this shows that tw is open. Okay. So tw is open. This is how we show the other direction. So in this case, the t, we show that t is open mapping if and only if 0 is the interior point of the image of B01. Okay, then from here, things become easy. We just need to show that 0 is the interior point of TB01, then it's done. Okay, or in other words, we just need to show this. Okay, so how do we show this? The first thing I'm going to show here, or this is in our second step, what I'm going to show you here is that there exists, we need to show that there exists some delta such that the U0 3 delta is inside the image of B01. Okay, if we can show this, this is done. But unfortunately, up to this, for this step, what we can do is to show this. Okay, is to show that the balls, this is the ball with centered at the origin with radius 3 delta. This is inside the y. I want to show that this is inside this closed ball, which is also in y. Okay, I first need to show this, and then the last step we're going to show that, show this one, here. Okay, so let's first show this, and here we're going to use the property that t is surjective. Okay, since t is surjective, we know that the tx is equal to y, right? But because y is Banach space, so it's a complete metric space, and this means that y is of second category. Okay, it's of second category. But on the other hand, we know that y can be written as the union of t of b0k. The reason is the union of b0k will cover the entire x. So the images of b0k's will also cover the y, right? Since the y is equal to t of x. So this is true. But since y is of second category, that means at least one of this is nowhere dense. At least one of this is not nowhere dense, because if every one of this, if this one is nowhere dense for every k, then y is of first category, which is a contradiction. So at least one of this is not nowhere dense. Okay, so So there exists some k such that the T of B0 k is not nowhere dense. While it is not nowhere dense means that the interior of the complement is not empty. So the interior of this B0K, T0K is not empty. Or in other words, there exists some white knot in the space Y, and also some R greater than 0, such that this Y knot is the interior point of that, or more specifically, the ball centered at Y naught with the radius R will be completely inside the TB0K complement. Okay, so we know that. But on the other hand, we know that if this, say if this is the 0, this here is the T of B0K. I know this one is symmetric in the sense that if there's some point, say Y naught in here, then the negative Y naught must be also in there, because T is a linear and it's mapping from a symmetric ball right here to this image. So if there's some point in here, that means this Y0 is equal to Tx naught for some x naught in this ball. Then the negative x naught will be also in that ball. So the T of negative of this, which will be just the negative of Y naught, will be also in here. And what we showed is this is completely inside this closed set. So this is, let's say this is the ball, the U, Y naught, R. And then this one will be also U, Y naught, R, but it's negative. Okay, so I know that both of these balls will be inside this image. Okay, so since T of B0K is symmetric, we know the U of Y, negative Y naught, and R is also inside T of B0K. Okay, so now I have this, then you can imagine that if I'm going to connect these two, by shifting from one to the other, I'm going to go through this middle one. So the average of the two, so what I meant by here is the U of 0R, which is inside this, meaning that for each point in this ball centered at the origin with the radius R, it can be written as some element from this ball and some element from the other ball, and take the average of the two. I should say this. Okay, this is because that we're in a linear space Y. So this is why this is true, and this is inside that inside this. Okay. So now since we have this, we can scale both sides by k, and by letting this delta to be R over 3k, we know apparently R equals to, so R over k equals to 3 delta. And as we said, when we scale down both sides by R, sorry, by k, scale down both sides by k, then we'll have u of 0 r over k, and this, as we said, is just the u of 0 with the radius 3 delta. This should be inside the TB01 closure. Okay, that's what we claimed that we're trying to prove. Okay, so that shows it. So there exists some delta such that this is inside there. Okay, I do need the 3 delta, but I want to do it more convenient in the next step, so that I actually have the U0 delta inside the open, inside the image of B01 without a closure. And that is what we're going to do right now. So we need to show that U of 0 delta is inside T of B01. Okay, this is what we showed on the right hand side here. So what we're trying to prove. Now we want to prove it without the bar. Okay, we don't want the bar here. So this is just directly the image of B01. Okay, to this end, first we know that we can look at any point inside the U0 delta. And according to what we have in the step 2, this should be inside the T of B0 1/3 closure. Okay, that's what we proved before. Just to scale down the radius by 3. Okay, so what this means is Y is either in this set or on the boundary of the set, because the closure is just this plus the boundary. Okay, so that means Y0 is either in here or is a limit point of this set. So that means if I choose delta to delta over 3, so the Y naught is inside the ball, or Y naught is a limit point or accumulation point of this T of B0 1/3. Okay, therefore for delta over 3, which is a positive number, we know there exists, so for delta over 3, there exists some x1 inside the B0 1/3, such that the T of x1, which will be inside here, So because Y naught is either inside here or is a limit point of this, so I know that there exists Tx1 such that the distance between this and the Y naught is less than delta over 3. Okay, that's how we should the existence of this x1. And now with the x1, I can further show that, so for y1 equals to y naught minus tx1. So that means I want this, or negative of this, to be y1. So the y1 has a radius less than delta over 3. So for this point, I know that it is inside the inside the U0 delta over 3. And according to what do we have here, or what do we have here, so you can just divide both sides by, scale down the radius by 9. Then you have a 0 delta over 3, and here you have a T of B0 1 over 9. So this must be inside the T of B0 over 9. Again, closure. Okay, and from here, again, you can show that there exists some point x2 that is inside the ball 0, 1 over 9, such that the distance between ty2 and y1 is less than delta over 3 squared. Because this is the distance I want. So y1 is either already inside here, or is y1 is a limit point in here. So that's why I can find this point that is this close to the y1. Okay, and now you can see we're going to continue doing so. So we continue doing so, then we'll have say the yk is going to be the yk minus 1 as txk, just by following this with 1 equals to k now. That will be inside u0, 1, or 0 delta over 3 to the k, which is inside t of b0, 1 over 3 to the power k plus 1. Closure. So for this, there we know there exists xk plus 1, which is inside above 0, 1 over 3k plus 1. So this is in here, such that the distance between this txk plus 1 and the yk is less than delta over 3 to the k plus 1. Okay, so do this for every k. And now we get a sequence of xk's. Okay, so note that the xk is inside the ball. That means the norm of xk is smaller than 1 over 3 to the k for any k. Okay, and then I know that but let the x naught to be the sum of them, okay, from 1 to infinity xk. Then you look at the norm of x naught. It will be by triangle inequality is bounded by the norm, the sum of the norms. But each of them is less than 1 over 3 to the k. And that is a geometrically decreasing sequence. And you know this one is equal to 1 over 3 divided by 1 minus 1 over 3. Okay, so this is the 1/2. So that means x naught, the series here is actually convergent, and the limit x naught is actually has a norm smaller than 1/2. So the so the x naught is inside the b0 1/2. Okay, this is something we know. Okay, that's what we have for the sequence xk. I'm also going to look at the sequence txk. Okay, so what is the sequence txk? According to our setup here, let's say the txk, if I move this to the left, then I will see the txk is just the yk minus 1 minus yk. Okay, so since txk equals to yk minus 1 minus yk, we know this is true for every k, right? So we know that the sum of from I from 1 to k for I from 1 to k of txi will be equal to, let's just take the sum on both sides, but for the right hand side there are lots of cancellations, and I will have the y naught minus yk. Okay, and this side here, because t is linear, so I'm going to move t outside, and I just have the t applied to the sum of xi for I from 1 to k. Okay, and I'm going to call this one the sk. Okay, so on the one hand, from the previous one, I showed that this is just a series of sk, or the sequence of sk. So that means this x there, 0 is just a limit of sk. That's what I know. But on the other hand, I know that the tsk, as I showed here, this whole left-hand side is just t of sk. So I know that the yk equals to y naught minus t of sk, right? I'm just moving this yk to the left and this to the right. So I have that yk equals this. So this is inside the ball, inside the ball u of 0. Let's see what it is. I should say, yeah, here. So this one here, according to our, let's say here, this yk is inside this. So each yk is in there. So this is inside delta over 3 to the k. Okay, but as you can see, when k gets to infinity, it's getting to infinity, this this yk will have a norm less than, so the norm of y0 minus t as k will be equal to the norm of yk, but it's less than delta over 3 to the k, so this goes to 0. And that means the y0 minus t as k goes to 0, or in other words, t as k goes to y naught or y0. Okay, that's what I know for the t as k. But on the other hand, as I said, this is just the limit of the sum, okay, from going to infinity. I is from 1 to k, and this is the xi. But this thing here is just equal to sk. So here it tells us that, on the other hand, I know that the sk goes to x naught. Okay, sk goes to x naught. Tsk goes to y naught. But t is continuous. Right? T is a continuous mapping, as we said. Right? T is a bounded linear operator, so it's continuous. So we know that the y naught is actually just a t x naught. Since t is inside here, we know tx naught is equal to y. Okay, but remember what is x naught? X naught is in here. So that means this tx naught must be inside, this one must be inside t of b0 1/2. Okay, and that means y must be in here. So y is in here. But this is inside t of b0 1. So that's why we showed that the limit, sorry, this would be y naught. The limit y naught here must be inside this. But on the other hand, we remember that this y naught is arbitrary from this set. So that means the u itself, since the y naught is arbitrary inside this ball, and we showed that this is inside b01 without the closure. And this completes our proof, which since we proved the right-hand side here, and this is equivalent to saying that T is open mapping, okay, as we showed in the step 1. So now this completes the proof of the open mapping theorem. And again, what this theorem tells us is that for any Banach spaces x and y, and any linear mapping T, bounded linear mapping T from x to y, as long as T is surjective, then T is open mapping. Okay, that completes the proof. So from here, we're going to prove the question we mentioned earlier. If we have bijection from we have a bounded linear mapping as a bijection from x to y, then the T will be open mapping, and we'll be able to show the T inverse, which exists since the T is a bijection. We'll be able to show that T inverse is also continuous. Okay, that means T inverse is actually from L, Y, X. Okay, we can show that T inverse is continuous. So proof is just using the result above. First of all, because T is bijective, so it must be surjective as well. And from there, we know that T is an open mapping. And also know that the U of 0, 1 will be inside the T of B 0, 1 over delta. Okay, I just scaled down. So let's complete the sentence here. So T is bijective, implies that T is surjective. It implies that the T is open mapping. And that also implies that, as we proved before, this implies that the U, there exists delta such that the U0 delta is inside the T of B0, 1. And now I just scale down both sides. There exists delta such that the U0, 1 is inside the T of B0, 1 over delta. Okay, just scale down both sides by delta. Okay, so that's what happens. And because T is a bijection, this implies that if I apply T inverse on both sides, then the T inverse of U0, 1 will be inside the T inverse applied to the image of B0, 1 over delta will be just the original set, which is B0, 1 over delta. Okay, so that I'll know this. And what this tells us, so now from here, we know that this tells us that for any y inside U0, 1, that means that the y is a point in the space y, and the norm of y is less than 1. Okay, and this means that for any y here, there is the T inverse of that is less than, has a norm less than 1 over delta. Okay, and then from here, we can say that since we want to prove that T inverse is the T inverse must be, we want to show it's bounded. So now we show that for every y here, it is less than 1 over delta. So we don't know if T inverse is linear, is continuous or not. So we cannot directly say that the norm of T inverse is less than or equal to 1 over delta. But we can show that by looking at this. So say for any epsilon and a non-zero y, the y is in here, is non-zero. We know first of all, the y over the norm of y will be equal to 1, right? But I want it to be inside this open ball here, so I want to scale it down slightly greater than 1. So I divided the y over norm of y by 1 plus epsilon, where epsilon is a small number. So I know that the norm of this is equal to 1 over 1 plus epsilon. So that's why this will be inside here. So we know this is less than 1, and hence the T inverse applied to this point. So apparently it is linear, so I can just pull out the constant, which is 1 plus epsilon over the norm of y, and then the T inverse of y. I know that this will be less than 1 over delta. Okay, so I know this will be less than 1 over delta. And then I just need to move the things to the right. then we'll have T inverse applied to y, which is less than, say, 1 plus epsilon over delta times the y. Okay, so because this is true for every epsilon, this is true for every epsilon, so we know that the T inverse of y will be less than or equal to 1 over delta times the y. Okay, and this implies that the T inverse is actually bounded. The norm is bounded by 1 over delta. Okay, and it implies that the T inverse is continuous since it's bounded. So a T inverse is continuous. So this completes the proof. Okay, so I want to make a remark. As you can see in the proof of the open mapping theorem, see the requirement here, we need it to be surjective, or in other words, we want this y to be complete. Okay, if this actually what we needed is this second step here. We want to show that this tx is of a second category so that I can continue. So this is necessary. If tx is not second category, then the result may not be true. Okay, and here is guaranteed because the tx equals to y, and y is complete, so that's why the tx must be of second category. But if it's not, then we may not be able to get the result. For example, let's look at this. Look at this example. I have this x, which is the C01 space, and also y is the C01. Okay, and now let's consider. So both of them are with the standard norm here, which means that if I have any point x, which is a function, continuous function over the interval 0, 1, I'm going to define this to be the maximum of the xt. T is between 0 and 1. Okay, so that's the standard norm we know. And you know in this case, x and y are both complete metric spaces. Okay, and then define this linear mapping from x to y by the standard integral. So it's just the t of x. X is some point in the space x. I'm going to map it to a new function tx, and that's going to be the integral from 0 to t of x s ds. So apparently the tx is also a continuous function, but it's even better than continuous. It's c1. So the t of x is the functions that are c1 because the integrated one. So the tx is actually differentiable, okay, and the derivative is equal to x. So it's continuous differentiable, and also the x naught should be equal to 0. Because when we have the t equals to 0, you just have 0. Okay, so this will be the image of tx. Image of x. Okay. Well, this is not a this is a subset of the y apparently, but this is not of second category. Okay, and because in this case the t inverse, although it exists, but it's not continuous. Okay, now let's look at what the t inverse is. Note that the t inverse right now, the t is the integral, so the t inverse is actually derivative, taking derivative. Okay, so for any function, the tx in this, I'm going to apply the t inverse, like taking the derivative, and I will get back to the space, to the function in the space x. Okay, so that's my t inverse. But this t inverse is not continuous. The reason is, for example, if I look at this function, sine of k pi t, let's say I divide by k. This is my yk function. I'm going to define my yk of t to be this, which is c1, so which is in this tx, should I say. Right? Because as you can see, when t equals to 0, this is equal to 0, and apparently it's c1, it's in c1. Okay? So I look at this function. I know that the magnitude of this function is equal to 1 over k for each k, right? But look at the t inverse of yk. So the t inverse applied to yk, I know that it's going to take the derivative. T inverse applied to yk, just take the derivative of yk, and that becomes, as you can see, is cosine pi times cosine of k pi t. Okay, so this is in x. But you look at the magnitude of this function. This is equal to 1. Okay, so that means I have a sequence of functions of yk, and the yk converge to 0 as k goes to infinity. But the t inverse of yk stays as 1. And this means that t inverse is not continuous. Okay, you have a yk goes to 0, but the t inverse of yk is not going to 0, so the t inverse cannot be continuous. Okay, so this is a counterexample. If the tx is not a second category, we actually may not be able to show the t inverse is continuous. But this depends on what the norm we define here. If we use this norm, then we will have that happen. But if we provide a stronger norm, suppose we use the same x with this norm, but for the y, I use I should say, for the ty, I should say, so tx, I use a stronger norm. So what this stronger norm is? Remember that this norm is applied to any x in the space tx, which means that the x here is a differentiable, is c1, and x not is equal to 0. So let's define the norm here to be the maximum of the xt and the x prime of t. Okay, taking the maximum of these two, and then t is again from 0 to 1. So this is a stronger norm in the tx, because this one, as we showed before, is this one. It's this set here. Okay. So now in this space, the tx will be complete. Right? This will be complete, and then it is linear. It's a norm, the linear space, and it's complete under this norm here. So this is actually a Banach space. And then you consider T as a mapping from the X to this space. Then we can show that the T verse is continuous because it satisfies the Banach theorem we showed just now. Okay, and actually you can see this by looking at, say, for any y inside the Tx, we know that the T inverse of y is just equal to the y prime. So let's look at the norm of this. It's just the norm of y prime, right? Y prime. But because the definition of the one norm here, it must be less than or equal to the y one norm, right? Because this is taking the maximum of either the x or the derivative of x. So the derivative of y prime must be less than or equal to this. And this shows that the T inverse is continuous because it's bounded. The norm must be less than or equal to 1. Okay, another thing that we should notice is that in the proof of the open mapping theorem, we had the following result in the last step. So we show that the sk goes to x naught. So the sk is the sum of xi for I from 1 to k. Okay, so we showed that, and we also needed that. We also showed that the t of xk, sorry, t of sk goes to y naught. Okay, and then from there we say that the t of t of x naught should be equal to y naught. This is because the t is continuous, but we don't really need the continuity. We don't need that strong to have this to hold. We only need a weaker property, which is called closed. So as long as the operator is closed, not necessarily continuous, we can still have the result. So what is a closed operator? So the definition is this. So we have two metric spaces. So let's say x and y are metric spaces. Okay? And then we say that the operator t from x to y is called closed if xk goes to x naught, which is xk goes to x, and txk goes to y. These two together imply that tx equals to y. Okay, as long as this is true, we call as long as a sequence xk goes to x and txk goes to y imply that tx equals to y, we can call the t a closed operator. So as you can see here, if we have both of this, and as long as t is closed, we will have this. Okay, we don't really need t to be continuous. So let's see an example for a closed operator. So for example, we have we define x to be the C1, and then y to be the C. Okay, and let's say that t is d dt, okay, which is the derivative. So in both of these two spaces, we use the standard norm for the y. So the y, remember the standard norm in y is defined to be, say I have x, and it's just the maximum of xt for t between 0 and 1. Okay, and I'm going to use the same norm as in y. In the space x, same norm. But under this norm, this x is not complete, as we said, because you can have a sequence of C1 functions that they convert to a C function, not necessarily C1. So as you can see in this case, this is the B star space, and this is B space or Banach space, and now I have this T, and this is a mapping from the X to Y. Okay, and so in this case, you can see that when I have xk goes to x, and txk goes to y. So txk, remember that that's the derivative of xk. Okay, so if you have this, then it will imply that tx equals to y. Okay, because this t is a closed operator, and let's say y. So xk goes to x. You know, in this norm, under this norm or this norm, right here means that the convergence is uniform, right? You have a sequence of continuous functions that converge to x uniformly. So that's what the meaning is. On the other hand, I also have this converge to y uniformly. Okay, so from here you can see that when we have both of this, so xk prime goes to y, when I have both of this, then I can rewrite at xk for any t between 0 and 1, I can rewrite this as, or I can express xk of t as this, xk prime as ds. This is by fundamental theorem of calculus. Okay, I'll have that. And that xk goes to x uniformly means that on the left-hand side, I know that this goes to xt, and that this goes to x not x0. And on the right hand side, because this one goes to y uniformly, so this means that the integral also goes to the integral of y, which is this. Okay, so I have this as k goes to infinity, and this means that x of t minus x of naught equals to the integral of that. And as you can see from here, that the x is differentiable, and the derivative of x is equal to y. Okay, so this means that the derivative of x, which is tx, is equal to y. Okay, and this shows that. So this t is indeed a closed operator, but it's not continuous, as we showed before in the previous example. We know that the t is not a continuous operator. Okay, so we only need this operator to be closed to prove to get the same result. So recall that in the open mapping theorem, we said the original open mapping theorem requires this. We want the x and the y to be B-space. Okay, that's what we needed. And we also need this t to be bounded linear operator from x to y, right? And we also require that the tx equals to y, or the t is surjective. And with all these things, we can claim that the t is open mapping. Right? This is what the open mapping theorem tells us. So now we can make this weaker. We don't need this t to be bounded linear operator, or to be continuous linear operator. We just need to be linear and closed. So say now I have the t which is linear and closed. So you know that this is weaker than the being continuous or being bounded. And I also have the y, and now I also have the x. But right now, instead of considering t as a mapping from x to y, we know that t may only be applied to some subset of x. So we only consider the domain of t. So the t may not be applied. We may not be able to apply to every element in x, but to the domain, we'll be fine. For example, if x is the C01, t is the differential operator, then t can only be applied to the subset of x, which is a set of differentiable functions, right? So we can consider t as a mapping from dt to some subset in y. Okay, so in this case, we can say that we just follow the same proof as in the open mapping theorem. And then we will have the sk goes to x naught, and also the t sk goes to y naught. This is the same as before. But because t is closed, we can still claim that t of x naught equals to y naught. And this is what we need to finish the proof. Okay, and also remember that in this case, the x, although even if x is a Banach space, this itself is not. This is the subset of x, which may not be a Banach space, but this is still a linear normed linear space or normed vector space. But this could be a B star space. For example, the one example here. If we consider the original x, see the x naught, this is the original space, which is a C01, and in this case, this will be or at least the differentiable functions will be a subset of the x naught. So the domain of t will be just the subset of x naught, which is C01. So in that case, we will have a B star space. So this the domain of t is a B star space instead of a Banach space. But it's still okay as long as y is a Banach space. Okay, so that's some comments or remarks about the open mapping theorem. Okay. Now let's look at another result for Banach spaces. So let x and y be Banach spaces. Okay, and the t as a mapping from x to y is a linear and closed. Okay, so this is weaker than linear continuous. Okay? It's linear and closed. And let's say that the range or the image of X under the mapping T is of second category. So it's a subset of Y, and it is of the second category. Remember that it means that it cannot be written as a countable union of nowhere dense sets. Okay, but the second category in Y. Okay, and then we can claim two things. One thing is as before, the zero, we can claim that the zero is the interior point of the image of B01. Okay, another thing is that the T is actually surjective. Okay, so we actually can claim from here that the T is surjective. Okay, so the first thing is that T is surjective, or in other words, Tx is actually equal to Y. The second thing is that 0 is the interior point of the image of B01. Or in other words, we can rephrase this in different ways as we know now. So for any epsilon, there exists some delta that depends on the epsilon such that the unit ball centered at 0 with radius delta in the space Y is contained in the image of B0 epsilon. Okay, so we actually only need to show that we don't really need this. We just need to show that there exists some delta such that U0 delta is contained in TB01. Because if we have that, then for any epsilon, we just need to multiply this 1 by epsilon like that, and then this will have a epsilon times delta. So you can simplify it into the way, or as we did before. Just show that there exists delta such that U0 delta is inside B01. Okay, just like before. In this case, we know that this just means that 0 is the interior point of this image right here. Okay, so we can claim two things. And actually, the first thing is clear. The second thing is clear because this is the same as what we did in the open mapping theorem. Okay, we have everything we needed, as we said, as we remarked here, as long as the domain of T, which is this X right now, you have a Banach space, and you have this Y as a Banach space, and this T is a linear and closed, then we will have the same result as before. So the only thing that we need to, so in that case, we'll be able to prove this part. Okay, just with that, I can prove this part. The other thing we need is this first part. We need to show this. How do we show that is the Tx is actually equal to Y? So we just need to show that every element Y in the space Y, we can find some element X in the space X such that Tx equals to Y. Okay, so that's what we need. So first of all, you can see we only need to prove 1. Okay, so first of all, as you can see, the 0 must be, so 0 in Y must be in the Tx, okay, because T is linear and 0 is in X, so T0 must be equal to 0, and that is also in Y. Okay, so we will not worry about that case. So apparently 0 is in the Tx. Okay, so then for any Y in the space Y that is not 0, I want to show that there exists some X such that Tx equals to this Y. Okay, so how do we show that? Remember that for any this delta to be, so I'm actually using this case right here. So instead of using the first statement, I'm using this one. Okay, because as I said, they're the same. So let delta 1 to be a number between 0 and delta. And then you look at the Y divided by Y. I know that this is the vector that has a norm equal to 1. right? And then I multiply by delta 1. Then in this case, this will be inside the u0 delta because delta 1 is less than delta. Okay, I know this. And because I know this, I know that it is inside. So this point is in here, but this is included in here. Okay, so that means there exists some x in B0, 1 such that the Tx is equal to delta 1 y over the norm of y. Okay, so as you can see, because t is linear, I can simply move the constant or coefficients of the y on the right hand side to the left hand side. Then I will have this y divided by delta 1 times x equals to y. So this will be the point in the space x, okay? Because x is a linear space, and as long as x is in there, as we said, x is in the unit ball, then scaling x using this constant, it will be still in x, since x is a linear space. Okay, so that means this is an element such that Tx equals to y. Okay, so this proves the first claim that the image of x is actually just a 1. Okay. So now let's look at another result called the bounded linear transformation. Okay, so let's say we have a B star space. And we have also a Banach space. Okay. Let's say that T is a linear. Let's say T is, let's just say T is in L xy. It's a bounded linear operator. Okay, so in this case, the I should say the T may not be able to apply to any element in X. So there is a domain of T, which is a subset of X, that we can apply T to. Okay, so T is actually a mapping from the domain of T, which is a subset of X, to the space Y. Okay, so what I'm going to claim here is that we can actually extend this T to the closure of the domain. There exists the T1 that can be written as this. So the T1 is also a linear operator, and when we restrict the T1 is linear, and when we restrict T1 to the domain of T, it's the same as the original T, and also the T1 has the norm equal to the norm of T. Okay? So if you consider the T as a mapping from here to here is, so we show that the T can be extended to the closure of the dt, such that after extension, the T1 coincides with T on this set, and also the norm are the same. Okay, so that's what we're trying to prove. Okay, so proof is actually not difficult if you see some similar components as we used before, or similar tricks as we used before. So what we need to do here is to show that for any x in the closure, there exists, so now you know, because in the closure there exists a sequence xk, which is inside the dt, such that the xk converges to x, right? Because it's the closure. So x is either it's a point in dt or it's a limit point of dt. Okay, so we can find a sequence in dt such that they converge to the x. Okay, and because t is continuous, we know there exists the dt is continuous on here. We know there exists some m. So actually, this I can just say this m is the norm of t. Okay, it exists such that the tx has a norm less than or equal to m times x for any x in dt. Okay, so that means the t of xk plus p minus t of xk, because both of the x are in dt, so this is still in dt, then I'll apply t to them, t to the difference of them. That will be just this. I know that this is going to be less than or equal to m times xk plus p minus xk. Okay, and I know that since xk is convergent, so this is a Cauchy sequence, so that the right-hand side should go to 0 as k goes to infinity, no matter what the p is. So this means that this goes to 0 as k goes to infinity for any p, integer p, or natural number p. So that means the txk is Cauchy. Okay, and this Cauchy and this sequence in Y, and Y is Banach space, so it's complete. That means there exists some Y in the, since Y is complete, this means that there's some element in Y such that the txk converge to Y. Okay, so actually we can see that this, it doesn't really depend on what the choice of the sequence you have here, but it's just that the sequence, when it converts to x, then the t of this sequence, after the mapping of t, it will be still convergent, and they will converge some point y. And this y doesn't depend on the choice of the sequence here, but only depends on this x. So in this case, we can consider the mapping t1 to be, what is it? We can consider t1 as a mapping from x to y. Okay, so for any given x, in here, I'm going to define t1 of this x such that it is equal to y. Okay. Okay, so now you can see we can show several things. First thing is that the t1 will be the same as t when we restrict it to the domain of t. Okay, so we can see the first thing is that when we restrict the t1 to dt, it will be just the t itself. And this is pretty easy to show, as since the x is already in dt, then everything will be just the same as we had with t. So that's just the t itself. Second thing is to show that t1 is linear. And to show that, we need to show that the t1, when we apply it to the alpha 1, or say alpha x plus alpha prime x prime. So right now, the alpha prime are real numbers. The x and x prime are from the closure of dt. I want to show that this is actually equal to the, when we have to separate them to show that t1 is linear. So to show that, we know that this is equal to the limit of the t of, so I want, say I have x prime from dt closure. So there exists xk prime, which are two sequences in dt such that the xk convert to x and the xk prime convert to x prime, right? And that's what we know. So the t1 of this is equal to the t of alpha xk plus alpha prime xk prime. This is because t is linear. Okay, and we have linear space, so that's the same So these two are the same. And then we can see that the t is linear, so we can separate them. Now we have the t, so the limit of k goes to infinity of alpha t xk plus the alpha prime t xk prime. Okay, we'll have that, and the limit can be applied to each. So we have alpha times the limit of txk, but by definition, that's just the t1 of x, right? Because txk goes to x. So the limit of txk is just t1 of x plus t1 of x prime. So this shows that t1 is actually linear. Okay, and also we can show that. So we just need to show the last one. We want to show this. Okay, so we already showed that the t1 is an extension of that. So that means the norm of t1 must be greater than or equal to the norm of t. That's for sure, because t1 is an extension of t. But on the other hand, I also want to show that this is actually t1, the norm of t1 is also less than or equal to the norm of t. And to show that, we just need to look at t1 of x. Remember that this is equal to the norm of y. Okay, and this, as we said, this is the y is the limit of t xk. Again, the xk is a sequence in this is a sequence in dt that convert to some x in dt closure. The y is some point in the space y. Okay, so we know that this is the limit. The y is the limit of txk. Okay, and from here we know that this is less than or equal to the norm of t times the limit of xk, because the definition of the norm of operator. And also we know since xk goes to x, I know this thing here is just x. So this is equal to the t times the norm of x. So for any x in the closure of dt, we showed this. So this implies that the t1 has a norm less than or equal to t. So we have greater than or equal to t and less than or equal to t, so the two must be equal. Okay, so that's how we showed that the extension of t1 is also just the same, has the same norm as the original t. Okay, from here we actually can get a very simple corollary. So it says as follows. Suppose we have two norms on the linear space X. Okay, so now X can be equipped with either of these two norms, okay, and they will form a B star space, or norm the linear space. If X is complete, with respect to either of these two norms, or with respect to both norms, and we know that the one norm is stronger than the other. Say one is stronger than the first norm is stronger than the second norm. Then we can actually claim these two norms are equivalent. Or in other words, the second norm is also stronger than the first norm. Okay, so as long as you have a normed linear space and two norms are the space is complete with respect to either of these two norms, one is stronger than the other, then they're just equivalent. Okay, so the proof is pretty simple. We just use the result before. Now let's think this. We have the same space, but when we equip them with we equip it with the different norms, we have actually two B star spaces. So let's say I have a mapping, which is just identity. It's identity mapping from the first space to the second. Okay, identity mapping just to map the same the element to itself. Okay, and we also know that this is stronger than this. Okay, so now what do we can say? We can say that when we map any x to some element here, but it's still just x, but it's in the 2 norm space, using the 2 norm. So let's say that I of x 2 norm is just original x 2 norm, since I is identity, and because the first norm is stronger than the second norm, that means there exists some constant c such that this norm is stronger, is bigger than this. C times that the 1 norm is bigger than the 2 norm. Okay, this is because that this stronger than this. Okay, that's what we know. Okay, so this means that I is a bounded, apparently it's a linear, and it's bounded, as you can see here. So it's a bounded linear operator. And apparently I is so this implies that I is a bounded linear mapping from x to x itself. But remember that this is I should say that this one is with this 1 norm, and this one is with the second norm. Okay, and I is apparently linear, as we said. I is apparently bijective because it's just identity mapping. So as I is bijective, we know by the Banach theorem, we just showed above, the inverse of I, which is still I itself, is continuous and bounded. Okay, so this is actually linear. Maybe I should say this in this way. The x with the second norm back to the x with the first norm. Okay, so we know that. And then once we know that, we can say that the I inverse of x in the it's a mapping from here to here. So if I have x here, then I inverse of x will be there with the 1 norm. But this is equal to the x1 norm. And this is bounded, means that there exists some, say, m, such that this is less than or equal to this. Okay, for any x. And this means that the I inverse is also, well, this means that the second norm is also stronger than the first norm. Okay, so you have the first norm stronger than the second one in the condition, and also you showed that the second norm is stronger than the first norm, so that's why they are equivalent. Okay, let's finish the proof.